So this is actually this is a real definition of senioritis from Urban Dictionary. So what we're wondering is the first thing we're going to do is do a proof to see if these events are independent. In other words, does being female make you more or less likely to have senioritis? Is what this is asking. So what we do is it's independent if the probability of one event doesn't affect the other, that's how you know it's independent. And the best way to do that is to use formulas. So these are independent. I think this should make sense. These are independent if the probability of having senioritis, given that you're female, is the same as just in general the probability of having senioritis. If those probabilities are the same, exactly the same, then we say that those events are independent. So let's calculate each one separately and see if they're the same. That's all we have to do. So let's start with the easy one. What's the probability of senioritis just in general? How many people have senioritis? 18. And how many total people are there? Okay, so that's simple, right? That's just in general. Now we want to see if being female influences that. And if it does, then they're not independent. So remember the given that, let's review from last time. Since it's given that female, you immediately look in that column or row for that condition. We only use those numbers. We're not going to use any other numbers. So that is females with senioritis, there are 10. And what do we divide by? 23, yeah. So this is the only time I want you to simplify or write as a decimal, because those fractions are tricky to compare just by looking at them. So if they're identical, then we say the events are independent. Are those the same?
They're close.
They're close, but they're not quite. So are you more likely to have senioritis if you're female or less? It's smaller, so you're less. So the answer is no, they're not independent, because being female slightly lowers your probability of having senioritis. Slightly lowers probability of having senioritis. Okay, so that's how you prove events are independent. Now we're just gonna take this two-way table just to see that you can represent it two different ways, and we'll make a table out of it, and then we'll answer if the probability, if we just select two people that they have senioritis, what would that be? Even though we could do it without the tree, we'll just do it with the tree. Yeah, cut.
Since these numbers are so similar, and there's such a small amount of people being tested, do you think if they had a larger number, the numbers would even out?
It's possible. And that's a good thing to be thinking about. But we'll just use the numbers as they are, because we're not doing inferential statistics here. But that's great. So senioritis, no senioritis, there would be 18 over 40 and 22 over 40, right? If we just randomly pick a person, and those are the probabilities that they have senioritis or not. And then the second person is the second event, senioritis, not senioritis. So that would be, 17 over 39. And this has to add to 1, right? So this has to be 22 over 39. And it's out of 39 because there's one less person. So this is 18 over 39, and this is 21 over 39. So we're interested in which outcome, the first, second, third, or fourth, for probability both students suffer from senioritis. We just want which one? This one? First one, second, third, fourth? Yeah, first one. We want the first one has senioritis, and then the second one. So we simply multiply those together, right? Because it's and. So, 1840 times 17 over 39. And if you do that, and in decimal form, it'll be 0.196, which is decimal can be nicer because it's easier to make sense of. So there's about a 20% chance that both of those students will have senioritis. So moving right along. But the senioritis. Okay, this one I'm gonna show you a formula that you need to know. It's sort of given on the AP formula card, at least the form of it is. And so we're not going to do a tree diagram. We're going to go this way. We're going to do it this way. We're looking for the probability that if someone speeds, what's the probability they're also distracted? So we're looking for the probability they're a distracted driver, given that they speed, because that might go up. It might be higher than just if they're just distracted in general. So let's see. It actually does go up. So here's the formula. Okay, what you do when you want conditional probability with the formula is you do the probability that they're distracted and speed. But you have to divide by the given that condition, divided by the probability they speed. And we've kind of already actually done without even the formula. We've already talked about how to do this, right? Before I even gave you that formula. What is the probability they're distracted and speed? Distracted and speed is right here, 0.6. And then we divide, since the condition is that they speed, we have to divide by that row that has speeding, right? So divided by 0.78. And that gives us our answer. But you can see why the formula works. So it gives you 0.7, there's a higher chance, 77% chance, which kind of makes sense that it'd be higher than just 60%. But this formula is going to come into play in the next problem. But are there questions about that? So the formula is this, because we're gonna end up using it here. The formula is this: the probability that I just used, and we'll need it in a second. Probability of A given that B occurs. We'll add it to our notes, but let's just put it by the example. Is the probability of A and B, we're using the intersection symbol, over the condition. It's always the given that part that you divide by. That's the formula we just used, and we're going to use it in this problem. So we're going to set up the tree. What are the two conditions here? A player is either, the two conditions are they either are taking drugs or are not. So drugs or no drugs. And so what would the drugs be? Probability of taking drugs is 4%. So we'll leave it as 0.04. So therefore, this has to be 0.996. Okay. And the other condition is that they test positive or negative. So if you're taking drugs and you test positive, that's fine. But if you test negative, that's a false negative. And so we know that this one is 10%. This false negative right here, false negative is 10%. That goes right here. That's what a false negative means. You were taking drugs, but you got away with it. So that's 0.10. And then this has to be 90% because they have to add to 1, right? And then these are positive, negative. Where does the 5% go? False positive. Yeah, false positive is you weren't taking drugs, but the drug test said you were. So that's a 5% chance. So this is going to be 95%. So the probabilities for all these outcomes, if you wanted just any outcome, like what's the probability that someone takes drugs and tests positive, you would just multiply 0.04 times 0.90 and you would get let's just write all the outcomes here, 0.036. That you take drugs but you test negative, that you get away with it, it's not very high. It's only 0.4% or 0.004. The probability that you didn't take drugs but you tested positive is 0.048 if you just multiply. And if you multiply 0.96 times 0.95, that is 0.912. You didn't take drugs and you tested negative. So to double check ourselves, because it's easy to make mistakes on this, what should all these add up to? 1, right? Because you have to have one of those outcomes. So they add to 1, just FYI, to double check your work. Now, the good part is figuring out what we want to know, which is the probability that plenty of people who test positive actually use the drugs. So that's that you took drugs and you tested positive. What's the probability that you took drugs given that you tested positive, given that the outcome was that you tested positive? So what you do is, using the formula, right? It's the probability you took drugs and tested positive. So what's that? 0.036. We just got it from our tree. But you have to divide by the given that condition, which is that you tested positive. So how do we get that? There's 2 possibilities, right? Here and here. So there's 2 possibilities for that. This one, this route, or this route that you test positive. So you have to divide by whatever that probability is, which you would add those numbers. So you divide by 0.036 plus 0.048. And that will give you 0.429. So there's a 42.9% chance.